This episode of Igalia Chats is brought to you by Igalia, an open source consultancy with a proven track record of landing features in devices from XR to handheld, deep expertise with embedded devices, advancements in flagship web browsers, kernel contributions, and much more. To get in touch or to learn more, visit igalia.com.
Okay, hi, I'm Brian Kardell. I'm a developer advocate at Igalia.
And I'm Eric Meyer, also a developer advocate at Igalia, and we have a special guest today. Alex, please introduce yourself and let people know what you do.
Hi, I'm Alex Bradbury on the compilers team here at Igalia. I've been working primarily on RISC-V LLVM, where I guess I've been working with RISC-V for something like 10 years now, and about 15, 14 years with LLVM in some capacity.
And sorry, let me just ask, RISC-V and LLVM, what do those stand for people who have never heard of them?
Right. So I'll start with LLVM. So LLVM used to stand for low-level virtual machine. It now stands for nothing. It's just LLVM. So LLVM is a compiler framework, and it's kind of, as many of these software projects, it's kind of started with a narrower scope and has now grown so large that the initial kind of expansion doesn't really make sense. RISC-V is a instruction set architecture. So RISC stands for Reduced Instruction Set Computer. And it is a open standard instruction set architecture that's seen increasing adoption over kind of recent years.
Yeah, I know, like for me, I got my first computer when I was like 7 years old. It was a TI 994A. Did you have a home computer, Eric?
In terms of an actual like programmable computer, we got a Tandy Color Computer 1. I believe it was revision 1. It had
those are
8K of RAM and 8K of ROM.
Those were sold by Radio Shack. In the States.
Cool.
But there were a bunch. There were like a Commodore 64, and Atari had one, and then you had the Apple. And then when I got just a little bit older, I got a PC clone. I saved up and built it, and I guess 88 it would have been.
Yep.
This part of the x86 family, since then we've had like 8086, 286, 386, and then we switched to these words like Pentium. And I don't know. I am embarrassed to say that I generally only think about this when I'm buying hardware. And I've kind of thought about it very generically in these two worlds. Like there's like the PC world and the Mac world. But then like there's always been these words that fly around like ARM and RISC, and like I guess it's a little bit embarrassing to admit, but like I don't really know about them or what they're about, and like why should I even care? And every once in a while it gets like a little bit confusing for me because like I had a MacBook that had Intel inside. And then there were also this phase where there were like Apple Power PCs. And I was like, what does this mean?
Right.
So I'm really hoping that like Alex can help us demystify some of this. And I don't know, like, is it clear to you all these things? Or is it just me that feels like kind of a dummy with this stuff?
Well, I figure Alex is probably clear to Alex.
I guess I can try and demystify a little bit. I mean, fundamentally, your instruction set architecture is providing a kind of interface between the code that's running on your machine and the hardware on your processor. So it's defining things like the register set, the instructions it supports, but importantly, how those are encoded and what their semantics are. So, what they do when you run them. And it's probably not surprising. It's not something you have to think about all that much because if you kind of imagine some stack of interfaces or pieces or things that make up a modern computer, the instruction set architecture, it's not at the bottom, but somewhere quite a long way below the bits that you normally interact with, the web browser, the operating system, Android and user interface and the like. So it's, I guess, increasing, and especially now that I guess there's a smaller number of instruction set architectures that are out there in day-to-day use, which I think is something you were hinting at. It's not something that you think about all that often as to whether you go and buy a system that supports this particular, ISA A versus ISA B. You just go and buy, an Android phone or a laptop, and it just works. Though I guess on both the laptop and server side, that is a case where there's been kind of increasing diversity in recent years, because ARM on both the laptop and server space has been moving forwards with companies like Amazon deploying quite a lot of ARM CPUs in their AWS, and of course you mentioned MacBook that in recent years moved over to working on to using an ARM based design with the M1 and so on.
And an ARM based design, what?
So ARM
I have
is
2 of them.
Yeah, so ARM is both it's a company who produce an instruction set architecture, the ARM instruction set architecture, and they also license designs that implement that instruction set architecture. They're what we'd call a fabless semiconductor company, in that they don't produce their own chips; they license it, and then others, say Qualcomm or Samsung or others, produce chips using the design. It's a little bit complicated in the ARM case, because there are actually 2 types of ARM license. You can either license one of the designs that the ARM engineers produced, so you get the latest Cortex A whatever core design that their engineers have produced. You put it on your system on chip. Alternatively, there's the architectural license, which is what Apple has, where they are just taking the instruction set architecture, that interface, but then doing their own implementation. And with Apple, with the M1, when that kind of hit the market, that was a pretty big leap in performance versus what was available otherwise.
So you're saying Apple with the M1, but Google also has silicon, right? So is their silicon also ARM based?
So I think Google has, to my understanding, done some limited end user available silicon. I think some of the Pixel phones may have an SoC that was done by Google, but in partnership with another firm. I don't believe that was their own custom core design.
So would it be ARM based?
So on the Pixel phones, yes, that would be an ARM based CPU.
Okay, yeah, I have one of those actually. I had distilled this down into like Apple versus PC kind of in my mind. But so to be clear, we have these instruction set architectures. Basically, there's the 2 that we've been talking about, right? There's like Intel and ARM, and then there's RISC, right? Like the RISC architecture.
RISC-V, yeah.
RISC-V. Was there a RISC-4 and a RISC-3 and a RISC-2?
Yeah, so it was called RISC-V because it kind of came from a series of primarily research architectures, and so they kind of looked back and saw that this was actually the 5th one that they'd done. It came out of UC Berkeley. But I guess the RISC-V, there's a name, it mainly served to confuse people who aren't sure whether to pronounce it RISC-V or RISC-V.
So these are like very low level. Above, though, the assembly.
So no, so the essentially the assembly is basically how you would write something in your target instruction set architecture. So you write in the assembly, you'd use the what's called the mnemonics, so the names of the instructions along with the operands that they support. So say RISC-V, one of the most basic instructions would be add I for add an integer. So you might do add I and then the register you want to write the result to, name the 2 registers that you want to add, and then you'd put that in text form into your assembler. The assembler then produces a binary which encodes that instruction in the appropriate 32-bit encoding.
What I understand you're saying is that RISC-V is an assembly language.
Well, I'd say that to interact directly at the ISA level, you would write assembly language. Of course, nowadays we mostly rely on compilers, but if you want to see, so you write your hello world in C, you put it into a compiler like Clang or GCC, you can ask it to emit the assembly, and then that's where you'd see it's a different depending on which instruction set architecture you're targeting. You can ask it to emit the assembly for RISC-V or for x86 or for ARM, and you'd see that it's using different instructions at the assembly level, which are targeting the different instruction set architectures.
Okay. I sort of understand.
So these have to be made for the hardware, right? Like the hardware needs some kind of some way to communicate with the hardware, and so there are very few that you have, and they're basically these three. But I think also now we have like cards, like graphics cards that have their own chips on them, right?
Mm-hmm.
So can you mix them in the same device? Can you have like an ARM CPU with like a GPU that has like RISC-V?
Yeah, indeed. And I'd say, I think you said there, but maybe these three architectures, there's probably a few more that are still in fairly common use. But where you really see, or have historically seen, an explosion in them is all of the kind of extra bits of logic on a larger chip. So you might have an end user programmable core where you really, really care about the software support story, the software ecosystem. Is there if it's running something like Linux, you want to have a port of Debian for it and all the other major distros. You have to support decent compiler support and the like. And then for but then for other bits of the chip, like a kind of power management engine or things like that, you might just need, it's something which isn't directly exposed to the end user. It might be something that is used only internally by the hardware vendor. And then for them, you have more freedom in the instruction set architecture choice and the possibility to take something like an open standard like RISC-V and then make modifications to it when you need to for your own kind of custom needs. That has been or can be quite compelling. And so previously they might have had their own homegrown instruction set architecture for that, whereas now they at least can benefit from the kind of shared investment in baseline RISC-V support. And if they need anything that's any extra features, they can go and do it themselves. And I think at the RISC-V summit towards the end of last year, there was a keynote presentation there from NVIDIA who spoke a bit about using RISC-V in precisely that kind of use case. So it's if you're if you plug in your graphics card, it'll have a RISC-V core on there. You don't directly program it or have any direct interaction with it, but it's providing services as part of the wider GPU. And I think they mentioned a figure of expecting to ship 1 billion RISC-V cores over the course of 2024. So there's actually you think about buying a laptop and it's got a processor in it and maybe it's got 4 cores or 8 cores or 16 cores, but on a modern SoC, you typically have dozens upon dozens of processors just dotted all around for all the different subsystems on the chip that you don't directly interact with.
Sorry, SoC stands for...
Oh, sorry. A system on chip, so it's what you typically call a kind of highly integrated processor.
Okay. And you said end user programmable chips, cores?
Yeah, I suppose I really mean programmer there. So I mean, end user, not necessarily in the consumer sense, but really, what can I, as a developer, get access to? And so it might just be something that's, you could think of it, I guess maybe it's better to think of it in terms of levels of abstraction, where there's the kind of the documented and exposed instruction set architecture, say on an Intel chip, x86. But then even on an Intel chip, there'll be different bits of that design that have different ISAs purely for internal purposes, and they are, not exposed to you directly.
So I think when we first started talking about this, I was asking you questions, and you used this thing where you compared them, and you said like it's RISC versus CISC.
So yeah, historically there's been this branch between the reduced instruction set architectures, so RISC versus CISC, which are the complex instruction set architectures, where x86 would be an example. And the difference really is that for a CISC processor design or instruction set architecture, you might have fairly complex instructions that take many, many, many cycles to execute, whereas RISC is trying to kind of simplify the definition of each instruction. It's more reliant on compiler smarts to try and produce an efficient sequence of instructions. But it's also maybe where most of the it's also kind of the direction that most instruction set architectures have moved in overall. Like you might argue about, particularly with some of the later ARM instruction set extensions, to what degree they're starting to pull in CISC-like features. But I'd say that trying to perform a minimum unit of work within a single instruction has kind of caught on as a a main design principle.
Way back at the beginning of that, you said we're talking about these three, but there are some other ones that are popular too. So what are they? Because just to get this all straight in my mind, what words am I overloading? Which things am I not understanding? What are some other ones that I might also know?
Yeah, so I guess it depends on your definition of popularity, if you like. I suppose MIPS and PowerPC would be two which are waning in popularity, but still there. System Z from IBM, again, that's for the kind of, a fairly niche use case, but there's a Debian port for it, for instance. More recently, there's Lungsen from coming out of China, which has similar goals to RISC-V, really, but taking a slightly different approach. But yeah, and then within we said ARM, but there's actually multiple instruction architectures within that. There's the old 32-bit ARM, and then there's the 64-bit ARM, which is often called ARch64. But then if you start looking at things like microcontrollers, although those are largely moving towards ARM or sometimes 32-bit RISC-V, you still have stuff out there like AVR, like on some Arduino boards and things like that. So you might have seen some of those.
In trying to prepare a little bit for this, I found some thing that was like the history of all kinds of different computing stuff, and it went into basically very early computing, and it talked about how we wound up with what we wound up with. And I heard in that, I don't know if it's true because it's just one source of information, but I heard that sort of ultimately, like, the IBM PC kind of just picked a winner, and like they didn't invent it, they needed something that was commodity already, and that you could assemble easily, and that it won more because they picked it than because it was the best thing available or something, which sounds very business believable to me. So I don't know, do you know anything about that history? Like, because there's a follow-on to this that you can go ahead and also answer, which is like, why choose one versus the other, right? I mean, is it just like PC versus Mac, JavaScript versus TypeScript? Like, it's a lot of preference, are there like really solid reasons to choose one versus the other?
Okay, so I think there's fairly fundamental reasons to go with one versus another, particularly for RISC-V versus the proprietary instruction set architectures. So I think you're certainly right in that often you might choose, or there are many cases throughout computing history where a standard has won out, not because it's the best, but because it was there at the right time, and then there's just enough of there's enough buy-in that it's hard for anything else to take over. I think RISC-V is a well-designed instruction architecture. Maybe not. There might be a few things people change about it if they started again, but it's also, even if it wasn't a well-designed one, I think there would be a strong reason for people to move towards it, and it's the fact that it's offering it's an open standard, whereas the other instruction architectures are not. So with ARM, you have to go and pay a licensing fee for at least typically to license their cores. It's very hard or expensive to get a license to do your own core, and even then, you don't have the ability to, or you don't have much ability to add in your own custom extensions and the like. They're very keen to keep a handle on. They're very concerned about fragmentation, things like that. So they don't want to have all kinds of different ARM cores from different vendors being mutually incompatible. Same with x86. It's basically just AMD or Intel who have the ability to produce x86 chips for, I guess, AMD for some historical kind of lawsuit reasons that ended up with them both getting a license. And then, whereas I think the way that RISC-V has been pitched is to compare it to an open standard like HTTP or SQL, so to think of it in those kind of terms. So yes, there may be open source implementations, but there are also proprietary ones. And the point is that it's a standard interface that you can swap out a different component, either one you built in-house or one that you bought in externally. So you have this ability to kind of multi-source, to change things over time. And I said before also the ability to add in your own custom extensions, which sometimes it just, or often that just isn't possible with these other instruction set architectures. There are more niche ones that have had that ability, which have been proprietary, but then they suffer from having a limited amount of investment in things like compilers and tool chains. Whereas the idea of RISC-V is that you have a kind of common base, but then a whole bunch of standard extensions which you can opt into if your use case requires it, and then you can define your own custom extensions on top of that if you need to.
Okay, so the draw of RISC-V is that no one person owns it, and you can use it essentially at no cost.
Yeah, and so you can have access to, you can implement the standard at no cost. You may very well go and license a core from somebody else or buy a core from somebody else. In fact, I think most kind of shipping RISC-V silicon are currently with proprietary cores, even though there's quite a lot of open source core designs available. I was prior to Igalia, I co-founded Low Risk, which was working in that kind of space, working on open source RISC-V designs. And then I mentioned before the idea of extensions. If you go and look at the initial motivation behind RISC-V, they were very keen that you have a standard which scales down but also scales up. I think part of what we've been discussing, and maybe partly of one of the reasons it's so hard to, can be a bit difficult to discuss something like instruction set architecture, is because it's used across such a wide range of domains, all the way from from microcontrollers, from little tiny corners of cores that you don't really get access to, through to mobile phones, laptops, servers, more specialized use cases. So this is things that might be running Linux, all the way down to things that have a couple of kilobytes of memory and they're running some kind of standard, either a minimal real-time operating system or a basic state machine. And so the idea is that there's a core set of roughly, I think it's about 40, 50 instructions that you need to implement to be RISC-V compliant. But then there are a set of standard extensions which a core may choose to implement. And if it's running Linux, it would implement things like single and double precision floating point, integer multiply, a whole bunch of bit manipulation instructions you'd expect to see there. But then if you think back to these really, really teeny tiny cores, which have very specialized needs, they don't necessarily need that. But certainly, as with picking any component of a larger system, you need to look at your requirements and then what's on the market and how it can meet them. And the advantage of a open standard is that if there isn't something on the market which meets all the requirements, you may be able to customize something, build your own, or take an open source implementation and modify it. So there are all these options available to you, which may not have been available otherwise. We talked about how you often don't really think about the instruction set architecture, and I think typically, that's true, you don't. But it's also you don't see really any adoption of RISC-V on the server side so far, right? There are a few startups there who are working in that space, but as it stands right now, I can relatively easily go and rent a server that's got ARM CPUs by the hour. I think Amazon had a stat that 50% of the CPUs deployed within their fleet over the last however many years were using their Graviton ARM-based system. The same isn't yet true for RISC-V. And on the one hand, you do have concern about ecosystem compatibility, what software can you run, but then once you have the necessary software ported, you're typically not going to care what the underlying instruction set architecture is. If you're renting something like a database server as sold as a infrastructure as a service type role, you just care about how many operations it can run per second. It doesn't really matter what the underlying ISA is. You typically don't interact with machines at that level. So you can see that's kind of a route for alternative ISAs being adopted over time.
You talked about compatibility, but as I understand, we all use high level languages and then use Clang or something, right, to compile. So you could compile for any of the architectures, right? At least these three, you can cross compile to any of them. And is it incomplete? Like, are there things that you just can't do with one and can do with the other?
Yeah, I think so you're totally right in that you can take your C code and compile it for tether architecture. Often there'll be a little bit of porting work that's needed. If it did use any inline assembly or things like that, you need to dive in and adjust that. And then largely the work is kind of a long tail of support work. So you might run into, I'm a compiler developer. It'd be nice if compiler bugs didn't exist, but yep, they do. I've introduced a number of them myself and fixed a few, hopefully fixed more than I've written. So you will find issues where you try and cross compile a package and it's you try and run it, either the compiler crashes or you try and run it and there's a problem. So there's a porting effort. There's also things like, I mean, you mentioned that we're often using higher level languages. Those also need to be ported. So things like if you're running your JavaScript JIT, you've got Node.js embedding V8. V8 needs to have a RISC-V backend for it. There is at least some RISC-V support upstream in V8. How complete it is and how well performing it is, I don't know. But the same is true. You'd be looking for the same thing with Java and the C# .NET ecosystem and anything else you're looking to support. And then beyond that, there's just the packaging and support. So things like Debian, there's a RISC-V port, but it's not yet kind of at the official level, so it doesn't have the same level of support as for ARM and x86. So we're hoping that will change in the next release. Canonical have been putting out Ubuntu releases for RISC-V, but again, it's still like a kind of lower tier support architecture versus x86 and ARM. So it's there's no fundamental barrier. It is kind of just with quotation marks there, a bunch of engineering work to go through and actually kick the tires and make sure all this stuff is working and do the necessary packaging work and the like.
Yeah, I guess now that I think about it, it probably depends a lot on what you're building because, you're talking about these things and I'm, I wasn't even thinking, but of course, you need, depending on what you're building, you need, Red Hat or Debian or, some kind of high level operating system and then, a package manager and you have to have all that stuff compiled. And that's not just you doing the compiling, that's, other people creating the packages. And so, if there already was that ecosystem and you wanted to provide a spreadsheet application, that would be considerably easier than all the rest, right? So it's like getting a lot of that into the world in the first place is a little bit more complicated.
Yeah, and the the more kind of embedded systems you're maybe thinking about first, that's been the case or those have been the kind of systems where RISC-V has had the most rapid uptake, and probably for that reason, because you don't care about the wider software ecosystem. You have you have a often internally written piece of firmware for managing your cellular modem, whatever it is. It needs to run that, and if it does that, the chip does everything it needs to. So you have to care about all this porting.
Yeah, that is exactly what I was thinking of. I wasn't thinking of like desktops and things, but that's interesting when you bring it back to that I understand. So the other thing that I want to ask was the fact that, you said it hasn't been successful on the server side yet, right? Like it's not like you can go spin up a bunch of ARM VMs, whatever, but you don't see that happening with RISC-V. That's kind of surprising to me in the sense that, I mean, it's not given this thing that we just talked about, but it is surprising to me in the sense that where it's competing, as I understand, is like at a hardware level, right? Like you're creating some hardware that runs this instruction set, but creating hardware, I think, is expensive, and I think there are not that many places that do it, and they have lots of built-in things that advantage them in a way to be proprietary, would be my guess. And so the fact that it's succeeding in those areas and not on the server where, it has a bunch of other challenges that we would have to solve, but they all seem very solvable without those resources and infrastructure that you need to build chips and stuff?
Well, I guess fundamentally, if you have RISC-V on the server, you still need somebody to produce that chip, which is going to be require a huge amount of investment and be a very complicated design, plus needing all of the kind of software infrastructure work. So it's not so much RISC-V hasn't been successful on the server. It's more it's kind of too early in the story there. There's multiple startups who are working on devices in that area, like Mintana and Revos being two. But it's the RISC-V stated goal, as Krista put it, who's one of the creators of it, is to become the industry standard ISA for all computing devices, which is a very lofty goal. It's like a long way from there right now, but I don't see a reason why it can't get a foothold on within the server market over time. But it is something that does require time and investment, and as you said, it takes a lot of time to produce chips, and particularly very high-end server chips are massively more complicated to produce than, say, smaller microcontroller designs. So those are kind of factors that mean that it's going to take a bit longer for people to start producing this stuff and shipping it.
There's a disconnect in my head still around what we are and aren't talking about in terms of what does exist in the world, because you said there are these goals to be the standard architecture for all computing devices, which is like up there with like world peace. It's a lofty aim that probably we're not going to achieve, but we want to aim for. So can you buy a RISC-V computer today? Like, can you buy a piece of hardware that you can, if you wanted to build a server today, could you?
Yeah, so there are multiple things you can buy. So there's multiple development kits like Raspberry Pi style single board computers, like the Banana Pi F3 is one that a number of us working on RISC-V LLVM use, because it has kind of has full support for RISC-V vector instruction set architecture, which is where a lot of the compiler work is focused right now. But it's kind of something which gives you okay performance, but it's not something you'd be looking to stick in a server chassis and expect reasonable performance and expect to get solid results out of versus a higher end x86. But it's definitely super helpful for initial porting and experimentation work. And then there's some companies out there who have put that chip in like the tablet form factor or a laptop form factor. So you definitely can go and buy this stuff. It's just at the level where it's a kind of a fun thing to play with as a hobbyist.
Yeah, because there's not the same kind of end user ecosystem, as we said, right? There's no...
Both the ecosystem and the core designs themselves are typically not at a design point that's like the performance isn't you'd get higher performance out of Intel or ARM cores for those kind of devices based on the chips that are currently available.
Why is that?
I think just these companies are ramping up, so they're starting with. We kind of talked about the embedded use case as being an area where you have to worry less about compatibility. If you kind of think further up the stack, there's also use cases where, yes, it's running Linux, but maybe it's in a particular environment, like maybe it's in a router or a set-top box or something. And so I think that vendors are maybe moving up the stack in that way. So looking at, typically you don't have a system that's quite as high performance versus, a laptop or a high-end mobile phone. So I think it's just time really as these companies are developing their portfolio of products. They're typically not jumping straight to the highest possible performance one, which would be the highest amount of engineering effort and highest risk, both in terms of engineering risk of producing it in the first place, plus the risk of people actually buying it because of the software ecosystem maybe not being there yet.
So you also gave examples like I think it was NVIDIA and maybe Qualcomm were examples where they were talking about using RISC-V on.
Yeah, as part of larger systems. Yeah, I think Qualcomm, it must be many more by now, but yeah, towards the end of 2023, they said that they'd shipped 650 million RISC-V cores. And then I think the NVIDIA figure I mentioned was a billion RISC-V cores shipped in the last year.
So they must be quite performant for those tasks anyway.
Well, performant for the tasks they're used for, but it's I think NVIDIA have maybe said the most about their use case, and it's more kind of embedded cores as part of management engines within a larger system. I mean, there are multiple companies who are producing high-end RISC-V cores. It's just not yet at the point where I can go to Mouser or Amazon or whatever and buy one. But there's no fundamental limitation there. It's just not a part of the market that's developed to the point in which I can just go and hit the buy button and get one of the chips shipped to me.
One of the things that you mentioned at the beginning was LLVM. How does that relate to all of this?
That's a good question. So LLVM it's a compiler framework that I've been working with for a long time now, and I'd say that the link is basically any of these, whether it's ARM, whether it's Intel, whether it's RISC-V, whatever chip you have access to, it's not much good unless you can actually program it and run software on it. And naturally, that's where the compiler comes in, and you pass in your C or C++, your compiler generates hopefully high performance code that takes best advantage of the hardware that you have available. And so compilers like LLVM and GCC, they really complete the story by making your chip actually useful rather than just being a lump of silicon that sat there on your desk that you can't really do anything with. For LLVM in particular, we've kind of grown quite a large contributor community to that over the past 9 or 10 years that we've been working on RISC-V LLVM things for a number of reasons, really. I'd say LLVM has had more and more interest from both companies and academia as being easier to modify versus GCC. So the GCC being the GNU compiler that's often the default on Linux distributions. But so it's for things like working with new, maybe more novel instruction set extensions. RISC-V vector instruction set extension is an example of that, where it has this concept of being length agnostic. So rather than hard coding a particular length of your vector, it's something that you can modify it at runtime, and which the compiler can try and make use of this. There are features like this where having an easier to hack on code base obviously makes it much easier to iterate on designs there and try out new things. Separately, LLVM is under a permissive license, so it's under an Apache style license versus GCC's GPL, and so that's another reason that there's been more and more corporate interest. And also LLVM acts as the standard backend for newer programming languages like Rust or Swift, and so if you want to support those on RISC-V, then you need to ensure you have solid RISC-V LLVM support.
So because of our work here, we hear people talk about the Clang compiler all the time. And what's the relationship with Clang and LLVM?
Yeah, so Clang is a sub-project within LLVM. So LLVM you can think of as being a suite of toolchain components. So it has the Clang, which is a C and C++ front end. So that's a bit which takes in your C or C++ source code and then produces the LLVM intermediate representation, which is kind of the bit that then that you run all the optimizations on. There are a whole bunch of other sub-projects within LLVM these days, such as the linker, LLD, a debugger. There's even a libc, so a C library, libc++, which are things like the C++ headers. And then other newer sub-projects like MLIR, which provides a kind of new extensible approach to implementing your own intermediate representations and that kind of thing. So Clang is the user-facing piece that takes your C and C++ and puts it through the rest of the LLVM toolchain. So the bit which I work on primarily is on the LLVM side. It's the back end. So you have Clang going from C and C++ through to LLVM IR. You then have a bunch of mostly target independent passes which go and do optimizations to that. And then it passes through to the back end, which translates from LLVM intermediate representation to the assembly effectively for your target instruction set architecture, which is where it's naturally becomes more and more target dependent.
Okay, so we're going to go back to the put my dunce cap on because it's not a VM though, is it? Like, is it really a VM? Like, it's not a VM in the sense of like the Java virtual machine, right?
No, it's not a. So it's I guess so the intermediate representation that defines a kind of low-level language for things like reading and writing to memory, for performing arithmetic operations. So you could maybe look at that and compare it to something like JVM bytecode, or say the bytecode implementations that you'd have within a JavaScript JIT. But it isn't.
But isn't it more like WebAssembly?
Yeah.
Is that a better analogy?
Yes, I'd say that's probably a better analogy.
Okay.
The focus really is on providing a common intermediate but documented format for how that your input, whether it be C, Rust, or Fortran, or whatever, is converted into. You can then reuse as much as possible between all the different instruction, all the different backend targets. So as much as possible is running on that in a target independent way, perhaps querying the backend for every now and again for specifics it needs, and then you pass it through to the backend where it converts it to, selects the native instructions, so RISC-V or x86 or whatever.
But it's very widely used, right? Clang and LLVM.
Yes, very much so. So as I think
much more than RISC-V, you would say.
But I guess by definition, more people will be using Clang and LLVM in some way because it's used by so many of the other instruction set architectures. I think I mentioned, although there's work to have like a GCC based backend to Rust and also a crane lift based backend, which is another code generator that's maybe most commonly used with WebAssembly. LLVM is still the primary backend for Rust, and then you have various vendors like ARM's default compiler is derived from Clang and LLVM, and Clang and LLVM is the default compiler used for build to Chromium, I think on all platforms now. Firefox for all platforms now, I think, though some of the Linux distros still try and build it with GCC. So yes, very, very widely used and adopted.
It's used for WebKit as well, is it not?
I believe upstream WebKit, yes. I think our colleagues are... I'm not sure if they're still maintaining support for GCC alongside Clang for the WebKit port for embedded. I think Clang would be the primary compiler for WebKit as well.
I understand that, like, ARM 64 is related kind of mainly in name to the previous ARM, right? Like, it doesn't actually share an actual lineage somehow.
Yeah, basically essentially a new instruction set architecture. Yeah.
And is it similar with the Intel family? Like, at some point, like, we've not really been just slowly evolving the 8088 instruction set architecture. At some point, we jumped to 64-bit or something, some big...
I think that there was less reimagining on the x86 to x86-64 side. There's been more recent proposals from Intel that would be more radical changes to the x86 ISA, there's certainly it's a different compiler target. The 32-bit versus 64-bit x86.
Right. So my question is sort of like how long has each one been at it?
Yeah, I'm off the top of my head. I couldn't say quite how old the x86-64 was, but I think. ARM64 was probably announced a few years before RISC-V started appearing publicly. I guess it'd been under development for some years prior to that as well. So I think RISC-V, the precise date RISC-V started, it's a bit hard to pin down. I think coming out of the university, there have been students who are working on variants of it for some time, but it's around about 10 years ago when it became public, like they first had a public kind of workshop, and companies started announcing they were looking at it or doing things with it. So around about a decade there. But yeah, I think you're right that it's hard to look at another architecture and say, well, it took so long for that architecture, it'll take so long for RISC-V. And really, it all comes down to market forces and investment and how long it takes these things to coalesce. And it's not really it depends on use cases or other factors. Like there's been a very high profile court case between Qualcomm and ARM about an acquisition they had of the Nuvia core CPU design, and about whether the license that Nuvia had for the architectural license was transferable to Qualcomm or not. So you see, all of these kind of concerns. Some of them, they may lead to additional investment in alternatives, which are where you're not reliant on licensing the design or the ability to produce a design for a single company, where you're more in control of your own destiny, and you can just make use of the open standard.
It's about the same age as React, I guess.
Right.
I think my question is, what's next for RISC-V?
I'm a terrible person with predictions, but it does seem inevitable that RISC-V has had that uptake on the embedded side. It seems as though there's only going to be more of that over time. Maybe not so much the kind of end user or the programmer accessible embedded stuff. So it's there's if you go to a standard parts catalog like Mouser or RS or Element 14, you're going to be inundated with options for ARM microcontrollers and not have many for RISC-V. They'll have a few, but there's still all kinds of usage in that in that area that maybe aren't quite so end user available. It seems inevitable that with more and more companies working in that space, you'll have more support for higher performance Linux capable cores. It just seems as though that's a matter of time, with various startups trying to produce products in that area. I think what's particularly interesting to me, coming as a compilers person, it's about how you kind of further expand and mature that instruction set architecture design. So what things like, there's activities now like a scalar efficiency working group within the RISC-V International, which is a standards body, trying to bring vendors together to try and look for any gaps within the ISA design where, if we had a few additional instructions of a certain type, we might be able to generate better code and close any performance gap that might exist between similar designs that use, say, AArch64 versus RISC-V. So I think there's more work to be done there, and that's quite interesting. There's also things like security extensions, like with Cherry. It started off from the University of Cambridge and other collaborators being defined. It initially used like a 20-year-old MIPS design as a base because that was known to be out of patent. Then they had a version of it for ARM and for RISC-V. The ARM one was in collaboration with ARM through a government-funded program. But it looks like the RISC-V one is the one that's actually going to ship in the not too distant future, and there are companies who are interested. There's a project underway to try and standardize it, and that's an example of the kind of thing which you can do with an open instruction set architecture, because there's not a single gatekeeper who needs to decide, like, is this viable for everybody to adopt? You just need to have enough people interested for it to move forwards.
Well, that's an interesting thing that we didn't talk about, but I would be kind of interested to talk about briefly if we can, which is where is it standardized? Like where is that done, and how is it done? Like, what does the governance model look like?
Sure. So it's at the RISC-V International. It's a body that's kind of responsible for the ISA specification. They're headquartered in Switzerland. Companies pay to be a member. And if you're an individual, you can be a member for free. And then collaborate through technical working groups in order to make proposals for changes to the ISA, or you might propose a new working group to try and design a new extension. Ultimately, there's like a whole lot of documentation on all the processes that are used, but at the end of the day, once an extension has been kind of completed by the people who want to propose it, it's sent out for a vote for ratification, whereby the main technical body vote on it. It gets approved by the board of directors, and then it becomes an official RISC-V specification.
And how many extensions have gone through that process? Roughly, like, is it a 5, 50, 500?
Yeah, it must be somewhere like 50 to 100, I would think, because there's maybe a small number of larger extensions, and then there's a lot of extensions that end up being really quite small, particularly things like control registers and the like that operating systems might modify. So there's a large number of them, but in but with a whole range of complexity for different extensions. So some of them are huge, like the vector extension, whereas there are others which are defining only one or two instructions, or maybe no instructions. They're just defining a few control registers for things like performance monitoring and that kind of thing.
So you said like some of them are kind of huge, but does that make it RISC-Y?
No, I'd say it's some instructions, some extensions by their nature are just have a large number of operations. They're still hopefully designed to be, operations that are logically distinct and targetable by a compiler rather than needing to be kind of handwritten to reasonably produce them.
Are there like a number of organizations that are part of that really would like to help shape these things?
Yeah, so if you look at the RISC-V members list, then I think you can see a large number of companies there, and you do have companies like Qualcomm and Google and Nvidia and others who are kind of at the top tier membership. There's lots of people want to move the specs in the right direction. It's often difficult to kind of match that up with resources being committed, or particularly resources being committed at the right time. As with any specification work, it's very difficult to predict like what your return on investment might be, in that you could put a lot of time, but then if nobody's really ready to engage on that particular idea, it can be kind of lost. Or alternatively, you get a bit stuck with back and forth where one person has their view of how it should be done, and another company has their view. But we all hope that these things, work out well over time. I think probably it's a case that open standards, I think probably don't develop faster than closed standards. I'd say the time I've been involved in RISC-V, particularly on things like security extensions, ARM has moved a lot faster. But hopefully over time with an open standard like RISC-V, you get to a better endpoint, and also as things continue to grow and you have more contributors, there's probably scope for more things being standardized that just wouldn't have made the cut when you're kind of reliant on a single gatekeeper.
So it's been a really educational hour for me. So definitely thanks for your patience and our questions, which are probably considerably basic for you. But I learned a lot in the last hour or so. So thanks for coming on, Alex.
Thanks very much for having me.
Yeah. Thank you.